Today we're going to look at something called Rolle's theorem and mean value theorem. Both of these theorems are what we know as existence theorems in calculus, meaning they tell us something exists, but it doesn't necessarily tell me how to find the something that exists. And they become important because we can learn some things about functions from them. We also will use both of these, but the mean value theorem more so when we begin to prove things in calculus. That doesn't mean we won't use this in things in class today, but this one's really, really valuable when it comes to proving things in calculus later. So don't lose track of that mean value theorem. There's some setup to both of these, certain conditions that must be met before we can say the theorem might apply to a function. So we're going to look at Rolle's theorem first and see what happens with it. We will be considering on a plane for now. We have some function in that plane. So let's think about it this way. Let f of x be a function, or be defined, on the closed interval from a to b, and differentiable on the open interval from a to b, meaning we really don't know about the exact endpoints, but we will know about everything in between. Also, I hope you remember that if it's differentiable, that implies that it's also continuous across that interval. So when we write the word differentiable, we're saying it also is already continuous to make that happen. So that's another piece that you need to remember in there. With this happening, we're also going to have that where f of a is exactly equal to f of b. So the end point y numbers match. There's a lot of setup to this particular theorem. It says then there exists a c out of this interval, at least one, where the derivative evaluated at c is exactly 0. So there exists some number c in that interval from a to b. Might be more than one number, but at least one, where the derivative value of that c is exactly 0. And can you tell me again when I say the derivative equals 0, what are we talking about? When I say this, what am I saying? When you plug the c number into the derivative, I get an answer of 0. So what does that mean? Okay, remember this means slope.
That it's an extreme.
So that the slope is 0 means what kind of tangent line does it have?
Horizontal.
Horizontal tangent line. So that means you either have a maximum or a minimum. So on the picture, it looks something like this. Suppose there's my number A, there's my number B. And we have a particular y value right there. That is f of a. But according to the theorem, it also is the same thing as f of b. So that means that needs to be right here. For me to have a continuous function, if it starts there, if I go up and down and up and down and up and down, something like that, there are several spots in here that you'll notice have horizontal tangent lines. So any one of these spots, maybe it was that one right there, there's a c. Rolle's theorem says it exists, but it doesn't tell me how many of them exist. It just says there's at least one. My job next will be to find all of them in that interval. In this case, that's several. But if it just goes, say, up and back down, then there's only one and we find that point. It's like a parabola. It's like a vertex of a parabola. That's what it's telling. Okay? Two parts to this thing. You're going to be asked in your homework, part one is to say, does Rolle's theorem apply for this given interval? So what do you have to check to see if it really applies?
But I thought you said they were always
We have to first meet all these prior conditions. Once I meet all the prior conditions, then I know this has to be true. But I need to make sure I've got it defined on the interval, make sure it's differentiable on the interval, and what else?
That it's the same equation.
That the function values at the endpoints are the same y number. That's the part of the critical piece. These two aren't too bad, but this is what you're going to have to check. So you have to evaluate the endpoints of the interval. They match the same y's, and we say, yes, now Rolle's theorem applies, so I'm guaranteed at least one. Makes sense. Not a lot of head movement. I think you need to see one.
Yeah, can you see me?
Let's see one. Alright. Let's see, f of x is equal to 4x minus x squared, for x is an element of the interval from 0 to 4. That would do something for us, I think.
So we want to graph it first?
Don't have to graph it. We want to see, does Rolle's theorem apply to this function for this interval? So is it defined between 0 and 4?
Yes. Yes.
Yes. Is it differentiable between 0 and 4? Yes, it is. So that means it's continuous between 0 and 4. So then the question is, what is the value of the function at 0, and what is the value of the function at 4?
0 and 0.
So you plug 0 in here and you get 0. You plug 4 in here, you get 0 again. So now we've shown all three parts that we need to talk about for Rolle's theorem to apply. Rolle's theorem applies, and I'm guaranteed at least one number between 0 and 4 where the first derivative is equal to 0. So how do I find it? That means I need to actually take the derivative, set it equal to 0, and then hope I can have the algebra skills to solve the resulting derivative. I think in this case we're going to be okay. And there it tells me that that is 2. And 2 does fit within the interval. This is a parabola. It actually fits halfway in between the interval. Won't always be parabolas, so it won't always be halfway. But there's an example of it. You've got to find all the background first before we get to apply the theorem and say it does exist.
And do you have to go back and put it in?
No, I don't have to. It didn't ask for anything more than just say find the x at which I have that horizontal asymptote.
So
What it
we
says.
just write x equals 2.
Yes.
Done.
Yep.
Okay.
At this stage, you might say Rolle's theorem applies, and then we know I've got that value. For more complicated functions, what this amounts to is we're trying to find ways to not necessarily try to find zeros of a derivative if we know between a certain group of numbers they may not exist. It hopefully saves us time on more complicated functions. This is a very simple function from this perspective. Questions about mean value theorem? I'm sorry, Rolle's theorem. Mean value theorem comes next.